Hey guys, my name is Safi Ularafai, and it's my last year here at Montgomery College. Today I'll be presenting my research that I've been doing at NIST since August of 2019. So the title of my project is a novel hybrid of SLURM and Kubernetes for lightweight machine learning application launch. And yeah, it is a monstrosity of a title, but by the end it should all make sense because we're going to break it down piece by piece, and it's all going to come right back together. So first and foremost, I'd like to thank the people that made this possible. Dr. Bontemps and Dr. Tolliver, the organizers of the MC-NIST program, they've done so much for me, and they basically made this whole thing possible. I'd like to thank my mentor, Carl Spangler. He's a hardware guy, and he has so much knowledge, and his expansive knowledge has helped me learn so much about computer hardware and software. And he even taught me all that I know about Bash, which is a scripting language that I use extensively during my internship. My dad, he taught me computer hardware since I was in fourth grade, and I'm glad that he taught me all that he did. And my brother Wally, he taught me so much about neural networks and artificial intelligence, deep learning algorithms. Um, I'm glad he did that as well, and I'll be talking a lot about that today. So here's an outline of what we're going to talk about today. We're going to talk about something I think is really, really important, and which is neural networks. It's synonymous to the computer's brain, and it will eventually be the future of computational intelligence. So I think that's one major thing that that's one major takeaway of this presentation. Another thing we're going to talk about is Nisaba, which is actually a server at NIST, which my department basically built for another department. They needed machine learning servers, and we're going to talk about why they needed that. Uh, Another thing we'll be talking about is the wiki, which is one of the small projects that I uptook, and of course the big project, which just from the name is a big deal. I'll be breaking that up into multiple pieces so we can make more sense out of it. And last but not least, we'll talk about future steps. So machine learning is the future, and we know that given enough data, a computer can learn and do just about anything. Programmers have given computers the ability to learn and make well-informed decisions that even humans can't make. And just like humans, the faster the computer, the quicker the computer can make a decision. However, most computers are actually slow at learning and making these complex decisions. But why, you might ask? And the short answer is your computer is not fast enough to compute the math required for complex machine learning algorithms. But before discussing the math behind complex machine learning algorithms, we got to figure out what exactly is an example of a complex machine learning algorithm. Well, there's actually many, including random forests, decision trees, naive Bayes, and today we'll be talking about my personal favorite, which is neural networks. But before we dive into the deep end of algorithm analysis and the nitty-gritty math behind neural networks, I want you to remember this tidbit of information. This right here is something called a sigmoid function. And essentially, what it does is it takes any value between 0 and 1, any value between negative infinity to positive infinity, and maps it to a value between 0 and 1. For example, if we were to take 0 and plug it into this function as the x value, our y value would be 0.5. If we were to plug in 6, we get a value really close to 1. If we plugged in infinity, we get a value really close to 1 because this is an asymptote. It never crosses 1 and it never crosses 0. If we were to plug in negative infinity, likewise, asymptotically, it would approach 0. Now, this is actually called the sigmoid function, but this process, when you plug in a number into this function, it's called normalizing data. It's also called a normalizing function. Just remember this little bit of information. Now this right here is a neural network, and what it essentially does is it takes any given number of inputs, in this case 4 inputs, and it figures out a trend between the 4 inputs, and it determines an output. Now those lines between the input and the blue layer, the hidden layer, and the blue layer and the output layer, we're going to discuss those lines, but for now that's a mystery. Now this right here is a neuron. The neural network was actually discovered by a psychologist in 1958. His name was Frank Rosenblatt. And his knowledge and understanding of the human brain and the neuron is what inspired the neural network. So surprisingly, a computer scientist didn't really find the concept of a neural network. They basically expanded a psychologist's understanding of the brain. And just like our neural network, where we had the input layer, and we basically transform it into the hidden layer, and the hidden layer into the predicted output, our brain does the same thing. We go from the dendrite and send an electrical signal through the myelin sheet to the other end, and we send it through other dendrites and other myelin sheets, and eventually our brain understands and learns. And likewise, when we look back at this neural network, we see that when we plug in values for inputs, we can have multiple hidden layers which act like dendrites. And eventually we can store data and we can predict the output. And how, we're going to figure out through an example. So right here we have an example where we take 4 inputs, body mass index, caloric intake, gender, and age, and we use that to predict an output. In this case, whether someone tests positive or negative for symptoms of heart disease. So again, here's a neural network. This image is going to be recurring, this diagram. And here is an example neural network with some given inputs. And here is what our data would actually look like. 21 is a 21 body mass index. That's the measure. 3,000 is 3,000 calories caloric intake. 1 is male, and 17 is 17 years old. And basically, given this person, given these 4 inputs for this person, we're telling the neural network that they do not have heart disease. They do not show symptoms of heart disease, hence the 0 coming out of the output layer. Now we're going to figure out what exactly is going on between the layers. What are these lines? So it's actually rather simple. All it is matrix multiplication, and a lot of it. The lines in the middle are called weights, and they're random numbers. They're random numbers, and they're eventually changed throughout the process. But all we do is we take these random numbers and make a matrix, and we multiply it with the input layer, the 4 gray dots. And when we take the dot product of these 2 matrices, we get another matrix, and then we take that matrix and we normalize that matrix. And if we remember what normalizing is, it means that if we take any value between negative infinity to positive infinity, we take any value, we plug it into the normalizing function, and we get a value between 0 and 1. So every value, n1 through n5, in the hidden layer is going to be a value between 0 and 1. That is an important thing to remember. Now going from the hidden layer, from these 5 blue dots to this one, the output layer, which is the 1 red dot, we also have to do matrix multiplication once more. And this time the matrix multiplication is obviously easier because we're downscaling the dimensionality of the matrix. So we're multiplying a 5 by 1 matrix by another 5 by 1 matrix, which is the random weights. We take the dot product, and obviously we get 1 output. And we normalize that output once more, meaning that we will always have a value between 0 and 1. Now, obviously, for any person, this process without numbers is really hard to understand. It's really hard to keep up with it. So together, we're actually going to run through this neural network process by hand. We're going to train ourselves like how a computer would, and we're going to do that for the first entry in our data set. So say hello to Doug, a 45-year-old male who eats 4,000 calories a day, has a BMI of 27, and has heart disease. So we know he's a 1, meaning he shows symptoms for heart disease. We're going to train this neural network to know that if it sees Doug's data, it will predict that he has heart disease. Or if it sees someone that has data similar to Doug's, it should predict that they also have heart disease. So this is our desired output. Given Doug's data, we want it to say that yes, in fact, that this person showcases symptoms or should showcase symptoms of heart disease. Now, we're going to do the matrix multiplication. So given our 4 inputs, body mass index, caloric intake, gender, age, we're gonna do the dot product with random weights, and I mean random weights can be random numbers, right? And I chose random numbers. I chose my favorite number. I chose 0. I love to see 0 anywhere in any math problem. I actually like to see anywhere except for on my tests. So I chose this 0 matrix. And if we take the dot product of the 0 matrix and the input layer, we get a 5 by 1 matrix full of zeros. And when we normalize the 0 matrix, we get 0.5. If you don't believe me, I got it here. We plug in 0 into the sigmoid, and we get 0.5, and I graphed it out there. Now, going from the hidden layer to the output layer, we have a matrix full of 0.5s from the hidden layer calculation we did. We also, again, I chose a random layer. I chose the random weights to be a 0 matrix again, and since we downscale the dimensionality with the dot product, we get 0. As our output, we normalize that, we get 0.5 once more. So we got a value of 0.5, which is a value between 0, which indicates no heart disease, and 1, which indicates heart disease. And we could round up and call it a day. But let's go ahead and do one more iteration. And this time, we will randomly change the random weights. Remember the 0 matrices? This time, we'll change them to random numbers. So I've chosen random numbers in here, and once more I take the dot product, and I go ahead and normalize that, and I get, again, a matrix with numbers between 0 and 1. Go ahead and take that matrix, I showed the normalizing process again just because. Go ahead and take that matrix, the hidden layer matrix, and then multiply by another set of random weights, and then I get an output, and then I normalize that output, and I get a value of 0.75, which is closer to 1. So what we're going to notice is that over time, this function will essentially optimize itself. It will keep on randomly changing the weights until it reaches a value that's very close to 1 or even 1. So it will optimize those weights to recognize that trend. And essentially what that looks like is an optimization process, which is being reflected right here. Over several generations, over several epoch, we call it in machine learning language, this function will optimize and it will get a brain of its own. And every time I see this GIF, it's staggering, and it's beautiful that the brain can store these trends within the randomized weights. Now, if we were to add more hidden layers, more of these blue layers you see here, essentially what would happen is we would have more space, more ability to store more complex trends. This is one of the most simplest neural network structures out there. I mean, just 4 inputs, 1 output, 1 hidden layer. The number of trends you can store in that is not that much, because you don't have that much space in those matrices to store the data of the trends between those numbers. But optimizing the number of hidden layers and is something called optimization of hyperparameters. And we won't be discussing that today, but since this is an introduction, but it's something that is a really prevalent part of my job. But yeah, you can see it once more. It's getting a brain of its own. It's beautiful. So yeah, we did it. We found a trend between BMI, caloric intake, gender, age, and heart disease. But this trend we found is only for Doug. We only trained for Doug's data. Now, what if we had to do this exact same thing, except with the data set consisting of 100,000 people, and we had to find the same trend? Humans are not nearly fast enough to calculate that. And even our computer CPUs are a little slow. However, GPUs are perfect. Obligatory Drake meme. I popped that in there. Now, for those of you who have come for an introduction for neural networks, this is where that ends. And now I'm picking up with why do we need Nisaba? Nisaba, as I alluded to earlier, is a new cluster, a new server, as you can say at NIST, which is specifically made to run complex machine learning applications, just like the ones we manually sifted through earlier. Now, Nisaba cluster is actually comprised of 2 NVIDIA DGX1 servers and it has a total of 16 NVIDIA V100 GPUs. Those are blazing fast GPUs. And DGX-1 is actually recorded to run machine learning applications up to 47 times faster than CPU counterpart clusters. Now, this is actually me running a machine learning application that I programmed on the server, and you'll see that it blazes right through it. It does 100 generations in less than a minute. So our process, we went through one generation manually for one data set for only Doug's entry, and it took us that long because we did all the math calculation by hand. But this trained through 100 generations of a massive data set in under a minute. So that's pretty impressive. Now, this is why we need the NIST server, to run large-scale machine learning applications with astounding potential. And since we're not currently on the NIST campus, my main task has been shifted to the wiki, which I'll be talking about. So this is an overview of my task just for reference, because this is where I'll be picking up into the work that I've done. The first is the wiki, and then next I'll talk about the big project. So the wiki, essentially, it's just dynamic documentation. It's made on GitLab, so if any of you have used GitHub, it's similar except a little more formal. It uses GitHub Markdown, if you're familiar with that, and essentially it's documentation. Although it's extensive documentation, it has machine learning tutorials on it too. It basically teaches all aspects of how to use Nisaba, and I've written several machine learning tutorials. I've used a variety of frameworks. I've used Keras, which is very powerful. TensorFlow, also very powerful. PyTorch and QPy. They're all very helpful tools to help craft the neural networks that we crafted by hand earlier. Now, just to emphasize how important these frameworks are that I made tutorials about, I programmed the example for Doug, which we did by hand, but I programmed that neural network by hand in Python. And it took me 3 hours without any frameworks, which is a lot of time. Here's the output. I was using my little brother's IDE, his PyCharm IDE, so hence the SpongeBob background. But basically, I basically programmed what we talked about earlier. We talked about the optimization of random weights to train the data set. And as you can see here, I gave it Doug's data, right? 27 BMI, 4,000 calories, male, 45 years old. I gave that as our training data. And then I gave it that same data to test. And it predicted it. The prediction was 1, which means that testing positive for symptoms of heart disease. And the expected was 1. And it took 3,000 iterations for the computer to figure that out. 3,000 epoch to go back and forth and then reach the desired output of 1. Now, the same program that took me a few hours to code would take a researcher using a framework just minutes. So here's a screenshot of the GitLab documentation. I can't really open it because I don't have access to it on this laptop. I'd have to access it through my work laptop, which would require some authentication, which I can't do right now. But anyway, it has a bunch of pages on it, and these pages have tutorials on how to use different kinds of machine learning frameworks. It has tutorials on how to use resource managers, which we're going to talk about. It has tutorials on how to use different sources out there on the internet in regards to machine learning applications. Now, these tutorials also enable researchers to utilize these tools, and that enables them to discover great trends in their data sets. And that is basically the seed, planting the seed for them to make great discoveries. And we know now that neural networks and machine learning applications are great, and they actually have amazing potential to make these discoveries. However, these neural networks are heavy applications and they take a lot of computer resources. And after all, I mean, we did see how computationally complex even the most simple neural network is. And for this reason, It is difficult for researchers to share their neural networks amongst each other. So there's the big problem. Researchers are having trouble sharing their machine learning projects. So my mentor Carl Spangler and I are currently working on a solution which enables researchers to share their work. And it's called a novel hybrid of SLURM and Kubernetes for lightweight machine learning application launch. We're going to break it down piece by piece. So we know what lightweight machine learning application launch is. We talked about machine learning applications, right? The neural network was the example that I gave. Turning it lightweight means that we have to make it less difficult. We have to make it more portable, in essence. That's what the part underlined in red means. Now we're going to figure out what SLURM is. It sounds like some kind of putty, or like Play-Doh or something like that. Some kind of jelly. Sounds weird. And Kubernetes, which sounds like some alien name. It's an interesting word, but they also do interesting things. Kubernetes is actually a container manager, and its purpose can be easily explained with an analogy. Now let's say you and your friend Doug, the same Doug from before, were eating at a table where no one can lift their plates. And now let's say that you're eating spaghetti, and Doug wants some of your spaghetti. It's a weird hypothetical, but trust me, it makes sense. Your first option is to transfer over the spaghetti with the fork and just cause a mess, spilling it all over the table. Or your second option is put all the spaghetti in a Tupperware and then hand the Tupperware over to Doug. You didn't lift your plate, you put it in a Tupperware and handed it over, and you're not making a mess. In this analogy, the spaghetti is the neural network, the messy neural network that's heavy and it's not really portable. And the Tupperware is a Docker container, which can be shared from researcher to researcher, or from you to Doug. Now Kubernetes basically ensures that this container reaches Doug. If the container fails to reach Doug in the first attempt, it will autonomously try again and again. Like for example, if you and Doug were sitting across a massive dinner table, and you were trying to reach across but you couldn't hand that container to Doug, then Kubernetes would ensure that you're trying your best. It will ensure that you try again to get that spaghetti container to reach Doug. The actual container itself is not Kubernetes. That is called a Docker container. In essence, Kubernetes is managing where the Tupperware goes and how it goes there. So Kubernetes is a container manager, and we can go ahead and substitute container manager for Kubernetes in our title to make it make a little more sense. So now we have to make sense of SLURM. What is SLURM? Now SLURM is a resource manager, and here's a clarifying example. Here's Nisaba. It's a blue box. Now if we take Nisaba, and if we had two people, one who wants to use Nisaba, half of Nisaba for 1 hour, indicated by the 1 in the green box, and another individual who wants to use the other half for 2 hours, indicated by the 2 in the red box, they can share it with an even split. Now, 1 hour later, half of the server is actually empty, and the other half is still being used by the person who requested 2 hours. And now, two other people, one who wants to use 1/4 of the cluster for 5 hours, and another who wants to use 1/4 for half an hour, can share the spot where formerly the person who wanted 1 hour was. So in essence, the resources are being split according to time. Dynamic resource allocation. And there you have it. SLURM is a resource manager. So we can go ahead and take our title one more time and splice that in there. So our title now becomes a novel hybrid of a resource manager and container manager for lightweight machine learning application launch. Now, Nisaba is completely assembled. However, the Kubernetes work has yet to be completed. We already finished the SLURM work, but because of the current circumstances, Nisaba is down and cannot be accessed until NIST is reopened. So I'm looking forward to when NIST reopens so I can go back and tinker with the Kubernetes stuff again. I hope that happens soon. But in the meanwhile, I'm working on the wiki from home, and I'm having a great time working with some of the neural networks that I've made, and it's been a blast. So now that's it for my project, and now it makes a lot more sense. It's Kubernetes and SLURM. In essence, when you make a hybrid of them, it's a novel hybrid of a resource manager and container manager for lightweight machine learning application launch. Thank you.